Good evening. I'm Yvonne Stapp, and I welcome you to Contemporary Science Issues and Innovations. Tonight, we catch up with the Large Hadron Collider at CERN as it closes down for a 2-year upgrade. Our guest, Markus Klute, is Associate Professor of Physics at MIT. Dr. Klute has extensive experience with particle colliders, beginning at Fermilab in Illinois while he was still a doctoral student, and then later moving to the Large Hadron Collider at CERN in Europe, where he's associated now. His team played a central role in the discovery of the Higgs boson, and he continues the effort to discover the most basic components of matter and possibly antimatter produced in the Big Bang. Tonight, Dr. Klute explains the complexity of producing the particle collisions and the analysis of particle data at the LHC. He'll tell us about the discovery of a possible new particle that awaits confirmation. Again, the LHC has just shut down for a 2-year upgrade, and we'll learn about the forthcoming changes as well. And in the meantime, we're very honored to welcome Professor Markus Klute.
Well, thank you for having me.
Yes, and I would like to get a little background to start with, please, in case it's unfamiliar. So, what is the Large Hadron Collider?
Well, the Large Hadron Collider is a large. It is located in Geneva in Switzerland. It's about 16 miles in circumference. And what we do there is we take protons. They come out of a bottle of hydrogen, basically. We accelerate them in electric and magnetic fields. Magnetic fields are used in order to keep the particles on a circular orbit. And then we bring them to collision at very, very high energy. What those collisions teach us is multiple things. We can use the particles at very high energies in order to probe small scales of matter. So we basically use the Large Hadron Collider as a very large microscope. We can look into matter very, very precisely. But as many viewers probably know, having a lot of energy available allows us to produce massive new particles. And that's what the machine, the key aspect of the machine is being able to probe the possible existence of new particles at very high mass scales.
May I ask about this now, when they say the new particles all the time like that? Is that a reconstruction of particles that existed in, say, the beginning of the universe, or something novel?
Perhaps. I mean, so maybe I should explain a little bit more what's happening inside the LHC. So at a number of collision points, we have 4 at the LHC. We bring those bunches of protons to collision. It's not just one proton on one proton, it's 10 to the 11 protons on 10 to 11 protons, and that about 40 million times per second. So there's a lot of proton-proton collisioning happening. And then we try to reconstruct with big cameras which look at those collisions what actually happens there. In case we produced a heavy new particle, we will find not the particle itself having an interaction with the detector, but this new particle most likely will immediately decay into multiple new particles, and those need to be reconstructed in order to figure out whether or not there is a signature of something exciting new. That's exactly how we discovered the Higgs boson by now about 6 years ago. The Higgs boson was produced in our collisions, and then the signature of the Higgs bosons was a pair of photons or a pair of electrons or muons, other particles in the detector. And then the measurement of the momentum and the energies of those particles allows us to reconstruct that there was a collision which resulted in a heavy new particle being created.
Okay. Now, the Higgs had been anticipated for a long time, but you're looking for even things you don't know about at this time, right? So I guess maybe we should back up and ask you about the Standard Model. Was that the thing that generated the questions in the first place? That what are we looking for? So like the Higgs was sort of predicted.
Yeah, so the Higgs boson itself was postulated in the 60s. The Standard Model then was actually put together in the years in the 70s and early 80s with ever more precise calculations which allow us then to test our data.
I see.
The Higgs boson itself was not discovered, and so there was an open question. There was a particle which was predicted by our standard theory, which was simply missing. And so the task of the LHC was to find this particle. That was a key task for which we built the accelerator. So now that we found this particle, we can ask whether or not more precise measurement of this new particle allow us to find possible deviations or a confirmation of our theory. And that's what we have been doing for the last 6 years. I mean, we have not been sitting on our hands at the
I
LHC,
know.
but we have more and more precise measurements. And my key research aspects are in the area of Higgs physics, so I'm trying to do a number of things. One is to probe the Higgs boson with more precision, so we make more precise measurement and try to test the particle. We try to find new properties or discover new properties of this particle. For example, whether or not there's decay modes which we have not anticipated, or we measure those we haven't seen yet. But there's extensions to the standard model which explain potential extensions of the standard model which explain to us potentially other phenomena in nature. And so one of those extensions, or many of those extensions, postulate additional Higgs bosons. So we have been trying to find those. We haven't seen them yet.
Yes.
So that's ongoing research.
But that sounds as though it takes such an enormous amount of time to get through that data all by itself. So you have these tremendous collisions, and you need this force in order to produce the particles. Is that it?
We have to produce in the order of 10 to the 11th collisions again in order to create one Higgs boson.
Isn't that something?
That's why we have, all those protons circling around in this tunnel and bringing them to collision at an enormous rate.
Yes.
Such that every now and then we produce a Higgs boson. Every now and then we produce something we might have not anticipated.
But it's not an
yet.
everyday thing. When you get this data, do you collect all of it, or do you pre-select what you're sort of looking for?
Yeah, so we produce collisions 40 million times per second. And each of those collisions is, each time when our camera makes a picture, we actually study in the order of 50 simultaneous collisions. On average, the number is about 38 right now. So we're looking at 38 proton-proton collisions with one shot of a camera. And we do this 40 million times per second. Now, one of those pictures of this camera would be 1 megabyte big. It's comparable with your camera you're taking your pictures. Now, we cannot store 40 million pictures per second. And most of them wouldn't be of interest. So we look for signatures of large energy depositions in our detector, or maybe a specific signature of a muon, some signatures of interest in our detector. And that helps us to decide whether or not we want to keep the event or just disregard it. And the trick is to get rid of everything which is not of interest as quickly as possible. We have a few microseconds time to make this kind of decision, and then only the remaining data is then collected. We have this early trigger stage, we call this triggering, we're selecting those events, is able to look more closely at about 100,000 events per second, 100 kilohertz. Those events are then read out of the detector, out of the camera, and put in a computing farm, which then allows us to look more precisely. So here we have about a millisecond time to look at those things. And we look for more complicated signatures. And about 1,000 of those events per second we record. We write them on a disk, and then we ship them around on the globe in order to further reconstruct, analyze, and understand what kind of physics is happening.
Now suppose you do find something interesting. Then, like when the Higgs first showed up, it really took a long time to confirm that. But you get something and it looks interesting. How do you confirm it? Will it show up again and again, or the use of these different detectors, are they involved in that? So you have the CNS and the Atlas and so on.
So we do statistical tests. We ask the question whether or not our background, in this case the standard model hypothesis, is consistent with the data. And only if the likelihood of that is very, very low, we claim that there's evidence for some new physics, or maybe an observation of some new physics. In that case, we would consult at CERN with the CERN management. We would also consult with the Atlas experiment in order to ask them to whether or not they can confirm or discredit our results or our findings. And that is a standard procedure. We make use of the fact that we do have two very similar but not quite the same experiments. So there are slightly different systematic effects, which from the way we detect, from the way we reconstruct the events. So we have this almost immediate proof whether or not our discovery is valid. In the case of the Higgs bosons, both the ATLAS and the CMS experiments, the collaborations made the discovery at almost exactly the same time. Even so, the detectors are very different. But it turned out that both of the designs used for the detectors yielded approximately the same sensitivity for the Higgs. That is not really a surprise because the LHC, but also the detectors were built with the Higgs boson in mind.
Yes, okay. What does a signature look like? I'm assuming that there's what I think it's been referred to as a bump.
Yes,
right?
So the signatures of new particles are typically bumps. So we have a spectrum of something in our data. This could be the mass calculated, reconstructed from 2 individual particles.
Okay.
Let's say 2 photons. The spectrum of standard model processes in which we record, they give us a distribution. This distribution might be flat, might be exponentially falling. In case of the Higgs boson, this was almost an exponentially falling distribution, and we looked for something, a deviation in this, a bump.
Okay.
Didn't quite know what the mass of this particle might be, so we had to scan this entire spectrum and try to find excesses of events, additional events, over this hypothesis of a background.
Okay, so once you get an image or this interesting data, there's a lot of work after that to make sure. And then you have, is it the 4, are they separate detectors? And you can confirm in that way.
So we have 2 experiments which are conceptually similar, and they have a wide range of physics interests and ideas. Those 2 have been used in order to discover the Higgs boson, the ATLAS experiment and the CMS experiment. Yes. We have 2 more dedicated experiments. One is called LHCb, and it tries to study as a main physics goal B mesons, and there's a question of CP violation of the symmetry between matter and antimatter is of essence.
So that's where they do that work, because I'd like to ask you about that.
And the other experiment then is ALICE, and ALICE is an experiment which is dedicated to the study not of protons and proton collisions, but to the collisions of lead and lead. Every year, at the end of the year, we take about a month out of this year to collide not protons with protons, but lead with lead. All 4 experiments can study those events, but the ALICE experiment is dedicated for this kind of physics.
I'm probably not clear on that when you say they use the lead. Is the nucleus then, the whole nucleus?
They use the whole
it's not just a proton.
It's not just a proton.
I see.
Many protons and many nuclei that brought together in order to...
heavy.
Exactly, and so the question here, the big physics question is the form of a new form of matter which we call a quark-gluon plasma. It's a plasma of freely flowing quarks and gluon, which is a study of the early universe in a sense where this kind of environment was present. So here, for a very short time, we create this new form of matter, and then we can study the property.
I see.
We learned, for example, that it behaves like an almost perfect liquid for a very short instant of time, but we can make.
But you can capture that at least, and this is similar to what you would have seen at the beginning of the universe. Then that property, whereas that's not the case with the proton-proton collision.
That's correct. So we use proton-proton collisions for the study of lead-lead collisions too. We just use this as a reference. We here compare. What would you expect when you have 2 nuclei collide to what happens when you have 2 lead nuclei collide?
Okay, so you have all this data, and now it seems as though you need these shutdowns in order to have the time to deal with the data. Can you give us an idea of what's involved with looking? Of course, I think people are aware that these are enormous teams of people.
So this shutdown specifically, we have about 2 years. Every single day of this year is planned for activities on the detector. So the CMS team, the experiment has a dedicated plan. We have this experiment in a collision hall. It's like a 3-story building.
Yeah.
It's very large and it's very heavy. It's as heavy as the Eiffel Tower. And so we have this experiment there, and we have to move pieces around in order to make changes to the inner parts of the detector. We have a small upgrade planned for the CMS detector, but just moving the pieces along, making sure that we don't break anything. Then
I can't imagine.
We have a short this update to one of our calorimeters, and then we have to put everything back together.
Okay.
But at the same time, the ATLAS experiment has an update. LHCb and ALICE have major upgrade to the detectors, and the LHC itself also will have a change to its injector chain in order to allow more intense collisions after the shutdown.
Okay. These things all involve matter, our standard matter, and is there anything to do with antimatter? I thought you alluded to that just briefly.
Yeah, so
will that show up?
When we collide protons matter with protons matter, we have some energy available, and that energy then forms into a pair of matter and antimatter.
Okay.
And so that's just standard physics which happens. And most of them we wouldn't
All
even
right,
call
like those images you see sometimes where, yes, okay.
So most of this is not really exciting, but what we can then do is we can study that some of this matter, those B mesons, they can form, they can oscillate between being in a matter state and an antimatter state.
Yeah.
And there is some symmetry between those oscillations, and that symmetry is very slightly broken. And measuring by how much it's broken is a very interesting question.
On that, this seems like a major question for the beginning of the universe. How did you get that asymmetry in the first place? Because we wouldn't be here, as they say, if we didn't have that. Then do you anticipate being able to answer that question down the line?
So we have strategies in order to, and we ask questions to our data. I didn't make nature, sorry, I'm just observing. So I think that the Higgs boson might have to tell us another story than just being that. So and when you just look at the zoo of potential,
I know that's
other models or extensions to our standard model, the Higgs boson plays a very prominent role there. And so it could actually be that there's a CP violating the CP is the symmetry I was talking about. Processes which violate the symmetry could happen in the decay of Higgs bosons. We're looking for those. But there's other mechanisms where this could happen. And in the US specifically, we have a large program of neutrino physics. This has nothing to do with the LHC, but there's a potential for discoveries as well in that area. And putting all this data, all this information together and forming the next step in our understanding is what we're trying to do here.
Do you think it's hard for people, and I included here scientists, there are scientists that are opposed to this big science stuff because it takes a lot of money and resources and so on. And of course, it's after these tremendous fundamental questions. Do you find that you're on the defensive about that at all, or do people really welcome it now?
Yes and no. I mean, we have to motivate our science, and the way we conduct our science is very different from small groups who have tabletop experiments where a small amount of money can answer one specific question. But we do have a very large program at CERN with our experiment, with my experiment, but also with the other experiment, which requires a lot of resources. But we do produce a lot of science. We have produced I don't know what the total number is, but in the order of 150 papers.
They're churned out constantly. The updates are.
So there's a constant production of new science coming out. Many of the results just say, we looked here and we didn't find anything exciting, but that is an increase in knowledge. That is interesting information.
Exactly. Can we go to what you do specifically, your particular interests in this? What do you focus on?
So there's the science part, the physics part of it, which has to do with really studying whether or not there are additional Higgs bosons, whether Higgs bosons have certain decay characteristics, comparing them with the expectation and learning about the Higgs boson that way. That's a key part of my research. But beyond that, I also make sure that we can actually analyze the data. So for the last couple of years, I was focused on making sure that we extract the best physics possible out of the data we take. And that has to do with calibrating the detector, with aligning the detector. I mean, we have a camera, right? And the camera takes pictures. It's not one picture, but many individual parts of a picture at the same time. One has to know very precisely to the micrometer level where the actual detector is. And so that is a detector which is as big as a large house. And there is a magnetic field which is turned on and off. There's metals involved, so things start moving. And we have to measure the movement. We also radiate our detector quite a bit while we have those proton-proton collisions going on. And one of the mechanisms which we use, we have a crystal in which we create light, and then the amount of light we create tells us how much energy the particles had initially.
Oh.
But when you measure light and you observe the light in this process, you might make a mistake in the actual measurement. And so when we radiate this crystal, it becomes darker and darker. And so we have to measure precisely how much light actually comes out of this crystal when we inject energy in the first place. So this is called a calibration, and this calibration has to happen constantly. The trick here is that
you have to keep
have to
recalibrate constantly, or
absolutely, in order to make the best measurements. If you don't do that, you smear the energy and you don't get a peak where you bump this, but you get a very broad axis, and that means that we have less information. We can potentially miss a discovery.
Yes. I was going to say, from the way you describe it, it sounds as though that would be one of the great anxieties, and that's an important part of the upgrade, I take it, is that to get it more precise all the time, because otherwise things disappear.
Right, and we have a program of upgrade to the detector which helps us to make slightly different measurements, which help us to make better measurements in the future. Also to collect more data at a certain amount of time. So as we look into the future, we have upgrades of the detector plant and the LHC, which allows us to take even more data at any certain moment in time, which means that the rate of acquisition of data increases. And that there's a number of challenges which come to this, which we are trying to address.
Yes. For the upgrade, the present upgrade, which is a 2-year span, right? What's happening at that during this time? What are they working on there? Because I understand there's another one coming.
Oh yeah, so there's
down the line that's even a larger time when it's down, and that's to enlarge the project.
So
right?
in this current round for my experiment, it's really changing some electronics and some readout of the calorimeters, for example, in order to. Again, the concept is we have particles, we stop particles in our detector and transform the energy in light. The more efficiently we get the light out, the more precise is our measurement.
Yes.
So we are changing the way we read out the light out of part of the detector in order to make better measurements.
Right.
But the next level of upgrade, which is planned from 2024 to 2026, is a much larger upgrade. So the machine, the LHC, will then be able to produce many more collisions as we have today, but the detectors will not be able to survive. There's radiation damage from those collisions happening, and we do need to replace part of the detector with components which are radiation safe, so they don't suffer in performance as we radiate them. So the current detector has not been designed for this, and therefore will also fail. So we have a program to upgrade specifically in those really radiation difficult environments. In the forward part of the detector, we will upgrade the detector, and also in the very central part of it.
So it sounds like there's a lot of innovation as you go here to you find, you have this problem with the radiation, and then you make these corrections, but then you get something a lot better. You really move substantially from there. Okay.
Absolutely.
All right.
We talked about the trigger before, right? So this upgraded detector will have a much more capable triggering system as well. So we can look at, not just coarse signatures in the detector, but we can measure the momentum of charged particle very precisely already on this trigger level, which then allows us to, select the interesting events more efficiently in the future. Or we can select them similarly as we do today, but in a much more difficult environment.
Yes. I think I read that you were planning to be designing a new detector. Is that correct?
So what we were thinking ahead. So when you look at the LHC, the concepts of the LHC have been pushed forward in the 80s. There was an initial meeting in Lausanne in 84. We took first collisions in 2009. It takes a lot of planning and foresight in this kind of large science in order to move the community and do enough research and
huge
development.
community.
So we are thinking right now, and we have been doing this for a while, what is the next project after the LHC? So for that we found an answer. That's the high luminosity LHC. So that's an extension of the program, and that's why we do these upgrades in 2024-26.
Okay.
This program is supposed to last and give us interesting physics to 2038. But then the question is, what happens afterwards? What are the questions we might not have answered then, but are interesting to follow up? What needs to happen between now and then in order to be able to, at least propose a new machine? And so we have been doing that in Europe, in the United States, also in China and Japan.
China's moving right along.
And all those programs are very international in the sense that those discussions don't happen in any vacuum. There is ideas for linear colliders for electrons and positrons. There is ideas for a similar concept to the LHC, but not with, now I have to talk in kilometers, not 26 kilometers, but 100 kilometers, 60 miles, I think.
Yes, something like whatever.
60
We're
miles.
going to catch up.
Circumference. This machine will then allow us to bring protons to collisions not at the current, just to give a number, 13 or 14 tera-electron volts, but maybe up to 100 tera-electron volts. So we almost go an order of magnitude in scales we are able to probe with these machines, and then ultimately answer questions whether or not dark matter exists in a particle.
That was the question next. Can you get really that far back? Can you reconstruct that very earliest universe from there? So you do anticipate that.
Dark matter is one of the big questions in fundamental physics right now, and the only evidence we have for this matter is through gravitational effect. So we look into the cosmos and we find that there is matter which doesn't interact with light. That's why it's called dark matter. And it's very fundamental to the formation of our universe.
Right.
We don't know what it is. There's no particle which, in our standard theory, which would explain this phenomena, which means that our understanding is clearly incomplete.
Yes.
So we might be able to find, even with the LHC, candidates for dark matter. We have other experiments where we look at the collision of dark matter with itself. There's an interesting experiment on the International Space Station, which is called AMS. They look for the remnants of a collision of dark matter with itself, which means an excess of antimatter particles are being detected by this experiment. That's exciting. They're still taking data on the International Space Station for this. There's also experiment underground which look for the collision of dark matter with some normal matter.
Yeah.
And so then you see signatures in your detectors of this kind of interaction.
Right. So
none of this has given us any clue for new physics.
Right,
There are some not fully explained results, so it's interesting to follow up on those, but we really need better ideas for detectors, and we need...
but it's a possibility that you are going to reconstruct that earliest stage of that first 3 minutes or whatever there, to be able to maybe detect this sort of thing, which is really...
It's not really necessary that we create this very hot and dense matter.
Right,
we just need to
pieces.
have... The reason why we haven't found dark matter can be either that we are not probing the right mass scale, or that the interaction is so weak that we do have to look at more collisions. So what we are trying to do is move in both directions. We're trying to probe higher mass scales, but we also try to take more collisions that we can probe very small interaction rates, meaning a very small number of events being created in our detector.
Yeah, but that's very exciting to think that they might really get a handle on things. You just to be able to go back at the beginning and find out where this dark matter stuff come from.
But just to give a few years for this. So we're planning projects which might start data taking in 2040, and then potentially take data for 10, 15, 20 years, so 2050, 60. So it's kind of interesting to think about what we might learn, what kind of technologies we might be able to use. Also defining a roadmap in order to develop the technology which makes this kind of physics possible. For example, the design of magnets which are able to give us extremely strong fields such that we can bend those protons in a circle, having those magnets being able to run at higher temperatures. Those magnets currently are used, other kind of magnets, weaker magnets, are used in any given hospital. So there is a real application of this.
Oh, I see, the downstream.
On the roadmap of our our
Yeah,
research, which is kind of, you can call it the fallout of our research, which has a real immediate impact for society.
I see. So you're part of this really interesting community. How did you get into this particle physics, I guess?
There's a number of points in my life where this, you can always say crossroads and you make decisions. One was my high school teacher getting me excited about particle physics. And he did this by bringing us to a museum in Germany, which is the German Museum of Science, if you want, in Munich. And there was an apparatus, which is basically a chamber which is filled with some fog, and you can see cosmic particles going through. And you can play games by putting a probe in front, and you create some interactions that way. And I just wanted to understand then how this works, and then we tried to rebuild one of those in our high school, which was fascinating. But then getting into this large science later on in my, then this was one of the key drivers for me to study physics, I think. But then getting involved in science at CERN as an undergraduate, I just started to love this international community. When I grew up in Germany, you're surrounded by Germans most of the time,
Yes,
but when you enter CERN, you're surrounded by people of all kinds of nations and backgrounds.
It's fabulous, isn't it? Yeah. That people can really come together and produce something.
I think it's because we define common goals.
Yes,
and then we work on those goals and forget a little bit the differences and cultural differences.
Right.
There's also a lot to be learned from different cultures in scientific process.
Yes.
The way we approach problems, the way we find solutions.
It can be very different.
Exactly.
And I realize that you are back and forth at CERN just constantly. Will that continue in the downtime here?
Yeah, so there's a big program of work between now and the next collisions.
Okay.
It has to do with preparing and looking again at the data we already collected, preparing the detector for the next phase. All of those are things, those 2 years that will pass by before we know.
They go very quickly. They go very quickly. And I imagine just getting through that data is a monumental job. So I think people get very excited with this, although it's a struggle to understand, especially when you see the extended pictures of the standard model anymore.
But I would argue that it's actually quite simple. There's only a few particles and a handful of interactions between those, or less than that even. When you look around, you see all this beautiful, diverse set of materials and colors. They're all made out of
Little
a couple of
tiny
quarks
things,
and an electron, really, and
Yes.
two interactions holding those things together. I think it's rather fascinating.
And beautiful, isn't it?
Exactly.
It really has a beauty to it, that all this design. But it is true, it wakes you up that you have, everything comes down to these few things, the few particles basically that make up an atom that then produce all the matter that we know. And so I can't wait to hear about the antimatter and other goodies that you will come up with in the future. Thank you very much for all the information.
Thank you for having me. Thank you.